Now let us study the liquefaction of gases. See, it's a very important phenomenon which was actual major factor which has resulted in the deviation or the study of the deviation of the behavior of ideal gases to the real gases. It was a major, it was the factor which has compelled us to think that yes, the gases are not ideal gases. Now liquefaction of gases means gases can be liquefied. Now gases can be liquefied. Gases can be liquefied by what? Putting high pressure and subjecting them to low temperature. So the two conditions are high pressure and low temperature. By putting up both these conditions, we can what? We can make this liquefaction process much more easier and simpler. Now this is what is the normal isotherm graph we are having for the liquefaction of CO2 gas. Now it's the liquefaction of CO2 gas, carbon dioxide. Now these are isotherms which has been plotted at different temperatures, T1, T2, T3, T4, T5, and it goes on increasing. Let at any temperature T1, the volume occupied by the gas was this much and the pressure was this much. When we started increasing the pressure in order to liquefy it, the volume decreases, so the graph is as the arrow shows, it goes like this. And suddenly at a particular pressure, the volume decreases drastically and a horizontal line comes on the isotherm. This horizontal line parallel to x-axis is an indication that the liquefaction process is going on. Before this it's a gas, and after this it's a liquid, and after this you keep on increasing the pressure. The compressibility of the liquid is not much, or the substance is not much. That means that shows that it has been turned into a liquid state. Now the same experiment is repeated at a little bit higher temperature T2. What we get is, yes, we get a same decrease in the volume, then there is a horizontal line, then there is an increase in the rate of pressure, but the volume doesn't get increased much, decreases much. But what we find is the length of this horizontal line gets decreases. It gets lesser than the earlier one at a lower temperature one. And if we keep on increasing the temperature and keep on plotting these isotherms, what we were always getting is the smaller and the smaller this horizontal line. Until a time comes, like at temperature T4, that this graph only touches if we join the ends of these horizontal lines, we will get almost a parabolic path. And what we find is this isotherm line at temperature T4 is only having a very small horizontal line, and after that it goes up, and this point, which becomes the peak of this parabolic path, is called critical temperature. We write it TC. So what is critical temperature? It is the temperature above which a gas cannot be liquefied whatever the higher pressure may be applied. Beyond this temperature you cannot liquefy the gas. The reason being its kinetic energy is always, this molecule's kinetic energy is always so much high, they will never settle down and they will never be liquefied. So a gas can only be liquefied only below its TC at this area. So the temperature which is required to, or temperature at which a gas becomes, above which the gas cannot be liquefied, whatever higher pressure may be applied, is called critical temperature. Now, whatever the pressure you uses at critical temperature is called critical pressure. Critical pressure. So the pressure applied to liquefy a gas at critical temperature is called critical pressure. Like for CO2 gas, this is 73 atm. And the critical temperature for CO2, as it is written here, it is 30.98 degrees Celsius. Now what is then VCs? The volume occupied by 1 mole of a gas at critical temperature. 1 mole of a gas, if when it is compressed at its critical temperature, whatever the volume it occupies is called critical volume. And in case of what? So this is critical volume. And in case of CO2, this is actually is 95.6 ml. So this is what we have, and with every gas shows this kind of a behavior. Every gas has its own TC, critical temperature, and this TC plays a very, very important role. Higher is the TC, more stronger the force of attraction a gas is having, more easily it can be liquefied. So remember, TC are directly related to your A, and this is directly related to your what? Liquification of gases. So which gas gets most easily liquefied, which is having the higher TC or higher A? We can put it directly proportional. Another important thing which is you need to know. Any substance above its critical temperature or TC can be called what? As gas. Below it, it is always called what? Vapor. We call it vapor. That's most important to note. At critical temperature, both liquid and the gas state coexist together. You cannot distinguish between the two, and that is why we use a term called fluids for that substance. You cannot distinguish between gaseous and the liquid state. And this is what we have, the phenomenon of liquefaction of gases.